Hello everyone, and welcome to this new video where we discuss mathematics and physics on the board. In today's video, what we are going to look at is basically continue some of the things we've done in complex analysis, where we defined essentially what we call an analytic function, and that's basically when you can express a map that goes from R2, so basically x and y, onto the complex numbers, and you can express that particular map as a function of the complex number z, which is equal to x plus iy. So this is some of the things we've seen before, so I'm going to put something in the description here, like some link here. And what we're going to see is basically what happens when we try to integrate basically a function around a singularity of that function. Okay, so we are not integrating across this particular singularity, but actually around it. And we are going to see that although it seems as if it's not a problem at face value, it turns out that actually it is one. So we are going to highlight what is the problem, and so why we can't basically use a kind of the simple thing, a simple trivial result that comes from any analytic function. And second, we are going to see basically one of the properties that arise from kind of looking at analytic functions in this particular situation. And then this is where we'll leave it for today. Okay, so as usual, just a bit of recap and context. So let's call here a map, and this map goes from R2, so it takes basically a pair of numbers x and y, and then it returns a complex number, which is essentially a sum of functions, so it's u of xy plus I vxy. Okay, now as it turns out, this is a perfectly valid map from one space to another space, which is not the same. Okay, this is a space of pairs of numbers, and this, in a sense, is a space of single numbers. Although they obviously you need two numbers to represent them, but the algebra is that of single numbers, if you will. And so these are two different spaces. Okay. And what we actually shown is that you can show that A can be essentially expressed as a single function, so a map from the complex numbers onto the complex numbers, f of z, and z here is a standard x plus iy. And so such a function is called analytic function in complex analysis. And this basically is only true if the u and v functions satisfy what are called the Cauchy-Riemann conditions or Cauchy-Riemann criteria. But whatever the case is, they need to satisfy this particular criteria. Okay, and if that's the case, then you've got a single function f of z characterizing your map A. Okay. So that's the first aspect that we discussed. Then what we showed actually, which was basically to try to do the other way around. So if you actually satisfy these kind of criteria, then essentially what you're going to get is that everything is as if there was a single function, f of z dz, that was kind of integrated. And so what we showed, in fact, is that if you've got some domain in the complex plane, and then you've got this map A of xy, but then you want to explore a path in the complex plane, then you can try to look at this particular integral and find that it's going to be zero for any domain omega. So this thing, by the way, is a border of the domain omega, is going to be zero for any such omega if this particular Cauchy-Riemann conditions hold. So essentially, if A is a function. And we're going to see another way of looking at it just in a few minutes. So that's basically where we left, and essentially this altogether basically present, at least in some form, this if and only if these conditions are satisfied. Okay, So now the question we want to ask is basically, what can I say about an integral like that? So I want to integrate here over the border of a domain. So here, this is something I'm representing here. So I put here the direction of integration along the contour. So here I'm integrating the circle here, just in case you haven't seen this notation before, means that this is a closed integral of a closed contour. Here, omega is the entirety of the domain, and within omega, there is z0, which is the thing here where when z is equal to z0, this is 0, and the whole thing blows up. Okay? F of z is a well-defined analytic function that actually is not singular anywhere in omega, and that is I don't think it matters much, but that is not 0 at z0, okay? So that's what we're going to assume, at least. So the bottom line is that what we're doing is that we're integrating this particular object. If I view that as a sum, I'm just integrating that over this particular contour here. And what we had seen is that, so first of all, what I can say is that the function, so f of z minus z0, is basically, I can say, is analytic in a sense on the path kind of d omega. Okay, so in a sense, there is only, there are problems. So what I mean by analytic here, you can conceive of differentiating these things, etc. There wouldn't be kind of any problem. But the only problem happens when you essentially have a z when you are at z0. Okay, so basically that's what we can say. So the thing is that I could imagine that if I integrate then a function that is this, and I'm not going anywhere close this kind of singular point, then I should be okay, and I should basically be able to use that particular equation. That if I can express that as a function of z, which basically is the case here, I can just say g of z is equal to f of z over z minus z0. I'm basically fine, okay? So basically, the question is, can I actually use that particular equation and that particular result that I should get 0? And so what I can ask here, is it 0? And so in fact, maybe that's not how I want to put it here. But so here I ask question mark, and question mark here could be, is it 0? And we need to understand why these integrals, when you integrate an analytic function, why actually it is 0. It's not the same thing as when you integrate something like df, for example, that is going to return simply a function that has the same value at initial point and the initial point. It's a slightly different trick. So here I just would like to remind, and that's something we used before, but from external calculus, if you've got a particular form here that you integrate, let's say, over some d omega, then we know that this is equal to d omega over omega, and that's on specific conditions. That's if, and that's something I've mentioned many times, if d omega is well defined in the entirety of omega. Okay, so if I assume this to be true, okay, then what I have is the following. If I imagine an integral that is like this, of something that is f of z dz, in fact, if you want, I can even say g of z dz, so that we are clear that this is relevant for what we want to say, then I've got the following. Let's apply naively this thing, okay? So I'm going to have, or at least let's apply as if this condition was met. So I'm going to have the integral over omega, so that's the domain that is basically bordered by d omega. So that's this domain here. And then I've got dg of z, wedge dz. Okay, that's basically, this d here is the exterior derivative. If you want, I will put some link somewhere where you can kind of have a look at what these exterior derivatives are. So this is the exterior derivative, but here in this particular case, and that's the exterior product. And then what we are going to get is the following. We are going to get dg dz, dz wedge dz. And if anything, you may remember this property of the exterior product, that if you take any differential and then wedge product with itself, then you get 0. So this is equal to 0. And so what that means is that the whole integral is 0. Okay, so that's why it works. And the logic of why it works is a little bit similar. In fact, it's quite similar to if you have, for example, a vector field that has a 0 curl, and you calculate the circulation of that vector field around a particular loop, then you can find that this is 0 by applying the Stokes theorem. Okay, and again, I can put a link. We've seen the Stokes theorem, in fact, a few weeks ago, or at least a few videos ago. So that's kind of the idea. But the big problem here is that this particular step is actually invalid if G is identified to being this thing here. And the reason why is because d omega has to be well defined in the entirety of the domain omega. Okay, and here I see that dg over dz in this particular case is going to blow up anyway at z equals z0, and so it's not well defined, and therefore I can't use this particular formula. Okay, so what happens is that I cannot use this formula, and so this formula can only be used in cases where you have a genuine g of z or f of z dz, and f is actually, and df, by the way, is well defined everywhere in omega. If that's not the case, again, you can't actually continue through, and you need to find some other ways to actually do that. So what I'm going to do here is basically try to present at least a property that we are going to use in order to evaluate integrals like that. Okay, so now we are ready. I've erased on that side, and I've redrawn slightly bigger this particular situation here. And then what I've done is the following. So I've represented the d omega, which is in black here, and that is surrounding the full domain. It's a compact domain, omega, that encloses, okay, that contains z0. So there is no problem. That's the very same issue as we've got here. Now, what I'm going to do is I'm going to essentially split or create a sort of different pathway, which is the following. I'm going to say that that basically I can create a path that sums up gamma 1. So gamma 1 goes from that point, then basically follows the entirety of d omega. So in fact, in my view, I'm going to say very soon that gamma 1 is basically d omega. So gamma 1 is in orange. I hope you don't have problems with visualizing colors or seeing colors. So here you've got gamma 1, but then what you do is that instead of continuing directly there, you take a very kind of steep path that is gamma 3 down. Then you go around the actual singularity, and then you go back via gamma 3 up, and then you continue closing the thing. Okay. Now, as it turns out, the loop or the domain that you've surrounded in that fashion, it's a bit sad that I've got to, yeah, it's the same color. It doesn't matter. But basically the domain that I'm surrounding via this colored path is this one. But you see that I'm avoiding the singularity here. So what happens is that if I apply that particular rule here, because within the domain that is surrounding here, so we can write that the integral of gamma 1 plus gamma 2, plus gamma 3 down plus gamma 2 plus gamma 3 up is equal, so of g of z dz is equal to some domain. So let's say that this domain, I'm going to call it omega, and then here let's call it omega dash, okay? And omega dash does not contain z0. That's what matters to us anyway. So I've got this, and basically that's equal to the integral of omega dash of dg wedge dz. And because dg here is well defined why? Because it's well defined everywhere within omega prime this time, because what is called the pole, so at z0 is actually avoided. The singularity is not there anymore when we integrate over the entirety of the domain. So it's actually going to be like this, okay? So that's actually great. Now, what I do is basically I split this integral into multiple parts. So I'm going to say, well, this is the integral of a gamma 1 of g of z dz, and then plus the integral of a gamma 3, let's say going down, g dz, plus the integral gamma 3 going up, g dz, and then plus the integral of a gamma 2 g dz, and all of that has to be equal to 0. Now, what you notice is that the actual path gamma 3 up and down, I can make them arbitrarily close to each other. And so I can make it so that these particular integrals, because you go one way and then the other, essentially exactly compensate each other. So essentially I can make it such that this is basically equal 0, okay, where they exactly compensate each other. And again, at least it's almost kind of there, like you take the limit when this tends to 0, okay, when the distance between these two lines tends to 0. And then where we are is basically we've got gamma 2 here, and gamma 1, I'm going to identify it when the limit of the distance between these two blue lines tends to 0. Gamma 1 becomes essentially, I'm going to write it, I can continue here, I think. I can identify gamma 1 to being d omega. And so what I end up having is basically the following. The integral of d omega, and here I'm going to imagine this is closed, and then g of z dz is equal to minus the integral of a gamma 2, g of z dz. Okay? But we have something that we need to consider. I actually chose a direction which conventionally tend to be the anti-clockwise direction for the orange curve, so for the d omega, the circulation around d omega. But I see that the circulation or the direction is inverted for gamma 2. So in fact, what I'm going to say is basically saying that I need to reverse gamma 2 here. So what I could say is that this is plus the integral of, in fact, any path. It doesn't depend on the shape so I'm just going to say gamma, that is g plus g of z dz. And if you want, but that's not necessarily, you can specify that the circulation has to be the same. One way here I decide to do it is basically by putting an arrow here, but that's not traditional, okay? Just to give the sense of the direction that we have. So the bottom line is that we've got a result here that g of z here is a function with a pole, okay? And what we have is that when you integrate with a singularity, when you integrate around the singularity, the fact that you're dealing with a function that has this pathological behavior only at z0 implies that the value of this integral actually does not depend on the shape of the curve of basically the integral you calculate. And so what people do, therefore, and that's a very, very important property, is that they're going to use whatever is convenient for them to evaluate that integral around that particular singular point. So that's basically, thanks to this property, that's where, again, I just want to emphasize, we absolutely need to be careful. This only works if d omega is well defined, which is not the case for dg in that case. And that's the only things I wanted to talk about today. In the next video on that topic, what we are going to look at is use what we've learned today to obtain or illustrate what is called the residue theorem in complex analysis, which is an incredibly powerful theorem in mathematics and in physics. Okay, so if you've got any questions or comments, by all means, do let me know in the comment section, and otherwise, see you in the next video.